Download this code from codegive.com, link in the description below. The perils of floating point imprecision in Python, and beyond. Python, like most programming languages, uses the ieee 754 standard for representing floating point numbers. This standard is incredibly efficient and allows us to represent a wide range of real numbers using a finite number of bits. However, it also introduces a subtle but crucial challenge: floating point imprecision. This tutorial delves deep into understanding this issue, its causes, and how it impacts your Python code, especially when dealing with mathematical operations. 1. What are floating point numbers? Before we dive into the imprecision, let's solidify what floating point numbers actually are. In essence, they're a way to approximate real numbers, like pi, square root 2, or even simple fractions like 1/3, using a format similar to scientific notation. Asterisk mantissa, significand represents the digits of the number. Asterisk exponent asterisk determines the magnitude, scale, of the number, how many places to shift the decimal point. Asterisk sign asterisk indicates whether the number is positive or negative. In Python, and most systems, the float data type typically uses 64 bits, double precision, to store these components. This allows for a significant level of precision and a large range of representable numbers. 2. The root of the problem: finite representation. The key concept to grasp is that computers have finite memory. This means we can only represent a limited number of values exactly. The ieee 754 standard uses a binary, base 2, system for representing floating point numbers. This is where the trouble starts. While some numbers can be perfectly represented in decimal, base 10, their binary representation can be infinite and repeating. Think of trying to represent 1/3 in decimal, you get 0.333333, which goes on forever. You can't store the exact value in a finite space. Similarly, many decimal fractions cannot be represented exactly in binary within the 64-bit constraint. 3. Illustrative code examples of imprecision. Let's see this imprecision in action with Python. In each of these examples, you'll notice that the results are not exactly what you might expect. The small deviations are due to the fact that the decimal numbers 0.1, 0.2, etc., cannot be perfectly represented in binary within the constraints of floating point representation. The errors can accumulate with repeated operations. 4. Why does this happen? A deeper dive. Let's try to understand what the computer does behind the scenes with 0.1. 1 decimal to binary conversion * Python attempts to convert the decimal 0.1 to its nearest binary equivalent. This binary representation is a repeating fraction, 0.000110011000110011. In base 2. 2 truncation / rounding * since the binary representation is infinite, the computer truncates, or rounds, it to fit within the 64-bit floating point format. This truncation introduces a tiny error. 3 arithmetic operations * when you perform operations like 0.1 plus 0.2, the computer operates on these slightly inaccurate binary representations. The error, though small individually, can propagate and become noticeable. 5. Consequences of floating point imprecision. Floating point imprecision can lead to various issues. Incorrect comparisons * direct comparisons using equals or equals between floating point numbers can be unreliable. Small differences due to imprecision can cause comparisons to fail even when the numbers are close enough. Asterisk cumulative errors. Asterisk in iterative calculations or simulations, small errors can accumulate over time, leading to significant deviations from the expected results. Asterisk unexpected behavior in financial calculations. Asterisk financial applications often require precise calculations. Even small rounding errors can lead to significant monetary discrepancies. Asterisk bugs in scientific simulations. Asterisk simulations that rely on accurate floating point computations can produce incorrect or misleading results. 6. Strategies for handling floating point imprecision. While you can't eliminate floating point imprecision entirely, you can mitigate its effects using several techniques. Asterisk use tolerance for comparisons. Asterisk instead of directly comparing floating point numbers, check if they are close enough within a certain tolerance, epsilon. Asterisk math.is close. Python 3.5 plus Python's math module provides a convenient is-close function for comparing floating point numbers with a specified relative and absolute tolerance. Asterisk rounding. Asterisk rounding the results to a specific number of decimal places can mask the imprecision for display or reporting purposes. However, be cautious when rounding intermediate values in calculations, as this can introduce its own errors. Asterisk decimal module. For precise decimal arithmetic, the decimal module provides a decimal data type that allows for arbitrary precision decimal arithmetic. This is particularly useful when accuracy is paramount, such as in financial calculations. However, decimal objects are generally slower than float objects. Asterisk fractions module. For rational numbers, if you're dealing with rational numbers, fractions, the fractions module provides a fraction data type that represents fractions exactly. Asterisk symbolic math libraries. Example SymPy for more complex mathematical operations where exact results are required. Consider using symbolic math libraries like SymPy. These libraries work with mathematical expressions symbolically, rather than numerically, allowing you to perform calculations without approximation. Asterisk careful algorithm design. Asterisk sometimes, you can restructure your algorithm to minimize the impact of floating point errors. For example, avoid subtracting nearly equal numbers, which can amplify errors. 7. When to worry, and when not to. Asterisk worry. Asterisk financial applications where precise calculations are mandatory. Asterisk scientific simulations that require high accuracy and stability. Asterisk algorithms that involve many iterations or complex mathematical operations. Asterisk comparisons between floating point numbers. Asterisk don't worry as much. Asterisk displaying results to the user, rounding is often sufficient. Asterisk applications where a small degree of error is acceptable, example some graphics applications. Asterisk when you're using integer data types for counting or indexing. 8. Key takeaways. Asterisk floating point imprecision is an inherent limitation of how computers represent real numbers using the ieee 754 standard. Asterisk it arises because decimal fractions cannot always be represented exactly in binary. Asterisk direct comparisons between floating point numbers are unreliable. Asterisk use tolerance-based comparisons, the math.is close function, or specialized data types like decimal or fraction when accuracy is crucial. Asterisk be mindful of cumulative errors in iterative calculations. Asterisk understand the limitations of floating point arithmetic and design your code accordingly. In conclusion, asterisk floating point imprecision is a reality in Python and other programming languages. By understanding its causes, potential consequences, and available mitigation techniques, you can write more robust and reliable code that handles numerical computations effectively. Don't assume that floating point results are always perfectly accurate, Instead, adopt a proactive approach to address this subtle but important issue. The best approach is to be aware of the potential for error and choose the appropriate data types and techniques for your specific application.